It's a beautiful Tuesday afternoon once again from 5 to 6 on this Mindset Tenfold Education Show. And I am Ms. King and we are doing all about physical sciences. And in today's show, we are doing a little bit more on the photoelectric effect, but now we are working in terms of graphs. So before we start the show, I just want to recap you based on what we did last week. So last week we learned about the photoelectric effect. We learned that if you want to eject electrons from a metal surface, we have to take into consideration the energy of the photon, the frequency of the photon, the different types of light that we can actually have, and then the kinetic energy that an electron can have. So in last week's show, we were given scenarios. From the scenario, we had to calculate the work function, the threshold frequency, and all that stuff. But like I always say, scientists are a bit lazy individuals, and then they also like summarizing things, whether in a graph or in a table, and then you have to use these two informations to answer questions. So in today's show, I want to show you what will happen if they actually give you a graph. So I'm going to show you what you need to look at when you have a graph. So make sure you have a notepad, some highlighters and stuff, because I'm just going to give you a quick scenario on how you actually maneuver the graph, and then we're actually going to answer a problem or a question together. It's actually fairly simple, but however, you must look into the picture. Remember they always say a picture has 1,000 words. It's the same thing in physical sciences. The diagrams that they give you will always have the answer. And something to always remember, guys, if they give you a table, or if they give you a graph, always make sure that all your answers actually come from the diagram that you're given. Don't go and outsource other answers that you don't have, and especially if they write it in bold, use the graph to answer the following questions. So without wasting any time, I'm first going to start with a scenario. So now we know that if we have a metal surface, and then we have some electrons that are there and so forth, and then we were to shine some light on these electrons. We know that the photon has to have energy, right? And the energy of the photon is dependent on HF, but then I can also say the energy of the photon and just break this up. Remember, I can say HC is over lambda. I just literally broke frequency into C over lambda. Now, we learned this in grade 10. But then I also know if this photon has got enough energy to actually emit the electron will be emitted, right? But taking into consideration, let me just erase this a little bit, that every metal, let me just write metal here, has got its own work function. What this means is that different metals will require different energies or amounts of energy and frequencies to actually emit the electrons. So something you need to remember, what will work for, let's say, potassium or cesium and so forth, will not be the same for both of them. So the work function and the threshold frequencies for the metals will then differ. So take that into consideration. So here we've got a photon, it has energy, we are able to emit an electron, and there we are, it has some energy. The energy of this electron, which we call the kinetic energy of the electron, is dependent on the energy that the photon has given this electron minus the work function. So for whatever is left, it gave it energy, however, some of the energy went to ejecting it from the metal surface, which we called our work function. And then whatever is left is the kinetic energy that the electrons have. Remember, the whole thing with the photoelectric effect, once we have actually emitted an electron, we want the electron to be excited. We want it to have energy so that it can actually move around. We don't just want the electron to have energy and go, bounce, okay, I managed to go up, and then no, we want them to have enough kinetic energy so we can actually generate a current. Now remember, these electrons need to have kinetic energy. It doesn't just come from somewhere. The photons will then give these electrons some kinetic energy to actually move around. So this is technically the scenario that we go about when we're doing the photoelectric effect in grade 12. So you can see I've drawn you a picture. But what scientists will do, they will give you a graph. I'm going to do exactly the same thing, but I'm going to explain what the graph says. So now, for example, if we are given a graph and they give you a graph like this, now we're also going to be mixing a lot of mathematics on this. And let's say on this side, they tell you this is the kinetic energy, which is the EK max. And then they're going to tell you on this side is FHZ. Now this is hertz. Now what you need to take into consideration, they can either ask you kinetic energy and frequency, kinetic energy and lambda, and so forth. But in most cases, they will tell you whether it's on the horizontal or the vertical plane, which is the y-axis or the x-axis. And then they're going to tell you this line is cutting somewhere like this. What this just technically means, if you're looking at this graph, here I've got a y-intercept. On this y-intercept, This will give me my threshold frequency, my work function. This is the minimum amount of energy required by the metal. And this we get on our y-intercept. Now remember, the y-intercept is when x is 0. This is what we get from mathematics. Where it cuts the x-axis. No, just take this as being an electron. It's on a metal. No. It must have enough energy to actually go above the metal. This is my threshold frequency, the minimum amount of frequency that is then required, right? And then we go up. Now, from mathematics, we know that a straight line graph is what we call a linear graph. I'm going to use the linear equation in conjunction with the kinetic energy equation, and then we're going to see how we move around. So now I've got the electron, and then I've got FO on this side. I just want to make this a little bit smaller so I got space. So now we know from mathematics, we have y is equal to mx plus c. When I'm looking at this equation, I can then say, remember, I'm looking at y, I'm looking at x, m being my gradient. I'm going to say Ke max is equal to, I can then say HF plus, or let's minus my work function. Remember, this and this can move around depending what you want to make the subject of the formula. So I'm just going to write the y-intercept gives you my work function. Your x-intercept gives you your threshold frequency. But then again, because we know that the photon will have some form of frequency, we can then say, we can look at lambda, my FO, and then my wavelength, right? And then something to also add on. If you are given y is equal to mx plus c, I'm looking at m. Remember, in mathematics, m is your gradient. In this case, m is my h. It's my h, which is Planck's constant. So to find my m in mathematics, we say change in y over change in x. Looking at this graph, my y is my EK, my kinetic energy, and my x is my frequency. Change in means 2 points, means I need to find 2 points that I need to work with. And then I can also add to say that my h is equal to delta EK over my frequency. And that is then how you can find Planck's constant. What they like doing, they're going to give you a graph. Then they're going to say, from the graph, calculate the work function. Now we know, finding the work function, I need to look at my x-intercept. Then they're going to say, find my threshold frequency. Then I know my threshold frequency, I need to look at my x-intercept, my y-intercept, depending on what they're asking. Then they're going to say, okay, but we want you to find Planck's constant. Using the y is equal to mx plus c, my m is exactly on the same position where my h is. So I know to find the gradient in mathematics, I take 2 points, delta x, delta y over delta x, and then I'm able to find h. We already know that the constant is 6.63 times 10 to the negative 34. So they would want you to prove that Planck's constant is this, but you need to use the graph. So first things first, if they do not give you a graph that's already drawn, you must draw a graph. Now, very crucial when drawing graphs, make sure that your points are accurate, because if they're not accurate, you are not going to get the correct answer. And then I'm also going to show you what is actually expected of you if you have to draw a graph or have to answer questions. Okay, let's just recap on whatever's happening here. So we have a photon that wants to emit an electron on a metal surface. The photon has to have enough energy to actually overcome the work function of the metal to actually emit or eject the electron. The electron needs to have kinetic energy, right? That is the scenario. Then we have to draw it on the graph. On the graph, we are able to identify the work function, the threshold frequency, and also prove Planck's constant, which is h, on the graph. How do we do this? If it is a straight line graph, according to mathematics, we are able to use a linear equation, which is y is equal to mx plus c. Whew, sounds like a mouthful. But if you can have all of this in your mind or next to you when we answer the next questions, you are good to go. So let's start with today's first question. So this question is from KG Moyla. And KG has given us this question and he wants us to help him answer it. Now, I wanted us to go through the graphs first before we can answer this question. So the question says, in an experiment to demonstrate the photoelectric effect, light of different wavelengths, so we can see light of different wavelengths. Now, I already know that wavelengths is represented by lambda, was shown onto a metal surface of a photoelectric cell. we have the maximum kinetic energy of the emitted electrons was determined for the various wavelengths and recorded in the table. So I can see, let's look at this table first. I can see the inverse of the wavelength. The word inverse is very crucial here because remember, if they say inverse, then it also means you can do the reciprocal or tip and tap. I can see it's 1 over lambda times 10 to the 6. Then I've got the maximum kinetic energy, and it is times 10 to the negative 19. Now remember, if ever you had to give the maximum kinetic energy, remember to say times 10 to the negative 6, because the examiner wants to see whether you actually understand that let's say the kinetic energy, you must say times 10 to the negative 19 in this case. It's exactly like saying when they have nanocoulombs or micro, mini, pico or whatever, and then you have to convert it to the correct value. It's exactly the same thing as conversion factors. Show the examiner that you understand that all these wavelengths are times 10 to the 6. So this is the table that we are given. Now let's see what our first question is. The first question says, what is meant by the term photoelectric effect? Now here they actually asked it a bit weird, not weirdly, but most of the time they're going to say define or what is the phenomena of the photoelectric effect, but also what is meant by the photoelectric effect. It means the definition for the photoelectric effect. Now remember, if you have to define something, it means it must not change. If you look in any textbook, it must always remain the same. It is the definition of the photoelectric effect. But however, if they say, please explain what you understand by the photoelectric effect, then it's based on your own discretion. If I can ask Mbali, what color is the background? She can say, oh, it's a dark shade of blue. But I can say, but it looks like it's sky blue. It's my own definition based on what I understand. What is meant, what is defined, the phenomena, the laws, and the principles is things that do not change. It must remain as it is in the textbook. The examiners actually just want to see whether you read your textbooks, number one. And unfortunately, if you want to branch off into courses of physics and chemistry, you need to know how to speak like a scientist. You need to know the genre that all scientists use. So in order to speak the lingo, you must know the definitions. So the first one, and this is for 2 marks, it says, what is meant by the term the photoelectric effect? So let's answer that one. This is 11.1. And we say, it is the process. Please don't write slang. It is a process whereby electrons are ejected from a metal surface and this is because when light, now remember, not all types of light of suitable frequency is incident on it. Now, if your teacher didn't teach you this specific definition, but they did teach you something else, most of the time when an examiner is marking, the memorandum might have 3 to 4 different ways that you could have said it, but they are looking for certain words. So don't say, electrons are when the photon comes and hits the electron. No, that is not what they are looking for. You have to have a certain meaning of what the photoelectric is for. But in this case, this is the one that I've chosen. Now, let's go to the next question. Our next question tells us we need to draw a graph, and usually if they draw, they actually give you graph paper. So now guys, in grade 12, if they tell you to draw a graph and they give you graph paper and you do not use the graph paper, it is not a good thing, right? Remember, they give you graph paper for a certain reason. It also means that you have to be accurate, and usually the graph paper has got blocks which helps you make all your drawings very accurate. So they're asking us that we need to draw a graph of kinetic friction on the y-axis. Remember, the y-axis is the one going like this, versus the inverse of the lambda on the x-axis, which is the one going like this, on the attached answer sheet. So now this is what we need to have, right? We need to have all of these on the answer sheet. However, let's first analyze what is going on here. Remember, if you are drawing a graph, we have to be consistent on how we number. You can't number 1 and then 15 and then 37 and then 14 and then 39 and then 100 and so forth. When we do graphs, you have to be consistent. It's either you count 1, 2, 3, 4 and so on, or you count in 3, 6, 9, 12 and so on. And remember what I always say, whatever you do for the horizontal plane, try to do it for the vertical plane, if you can. If not, make sure if you count in 2s this way, you count in 3s in this way, because you need to, it's all about accuracy, especially if you have to use the graph to answer more questions. So in this case, I can see I'm starting off at 2, 2.5, 3.3, 5. So you can count in 1s. And in this side, I start by 0 point something, then 1, 3, and 6. So you can also actually count in 1s or in halves. So in order for us not to waste time, my darlings, I actually took the graph from the memorandum that was given, but now we're going to analyze it. Just want to see for how many questions was this. So we have a graph, and this graph was for 3 marks. So let's see. Remember, you are always taught from grade 10, if you are drawing a graph, every graph needs a heading. In this case, we have the graph of the kinetic energy versus my lambda. That's what we were told. Where did you get this, Tobile? This is what I was told, that I was given kinetic energy and I was given my lambda. Please don't write the heading of the graph being electrons versus protons. No, that's not what the graph needs to be about. You also have to label your y-axis as well as your x-axis. It's also very important to actually show the examiner what you are measuring it in and give it an SI unit in both cases. As you can see, for the y-axis, I've counted in 2s. From my x-axis, I've counted in 1s. Now, very crucial. Most of you guys probably do know how, but let's do this quickly. Let's look at the first one. I remember my lambda is on my x, this is on my y. So on my x-axis, I need to find a 2, and then it joins with 0.7. Let's see here. On my x-axis, I have to have a 2. If I look at 0.7 something, it must be somewhere around there. So going on those with all of them, let me just look at another one. So I'm also going to look at this one here along with this one. Let's draw a heart this one. We'll go with this one. Let's put a star on this one and these ones. So these are the 2 points that will work hand in hand. It's also very crucial that you understand the points you're working with, because remember, if you have to find Planck's constant, which is delta y over delta x, you have to use 2 points that you have chosen in order to find those answers. So make sure if you have the x for the 1 point, you also have the y for the 1 point and so forth. So keep that in mind. But that's the case. This is the graph that you should come up with. I just didn't want to waste too much time on it. And then something to always remember, if you're drawing points like this, always find the line of best fit. It's very crucial, line of best fit. Also make sure that it touches the bottom, because this means that is where everything starts. So there we have our graph. Now let's see what is then expected of us from the graph that we're given. In capital letters, it says we must use the graph. This means do not go and calculate things that are not there. Then we have 11.3.1. It says use the graph and calculate the threshold frequency of the metal in the photoelectric effect. Now remember, the threshold frequency is FO, and remember the threshold frequency is the minimum frequency that is required to then eject the electron. But what did they tell us? We need to use the graph. I just want to quickly go to this, our first idea here. Remember, when we talk about frequency, we are talking about this one here, the minimum frequency that is required to actually eject that electron. I'm also going to take this into consideration, and then we'll take it from there. So let's answer our next question. We have to find the threshold frequency, and this will be 11.3.1. threshold frequency. Now remember, we have the formula Y is equal to mx plus c. Now from the graph that I'm given, I know I've got the energy on the 1, I've got my threshold, that's my work function, and then I've got my EK max. Now I'm going to break it up. Remember, if I'm looking for the energy, I can say HF is equal, looking for the work function, I know it's Planck's constant with the threshold frequency plus EK max. I have to break it up because I do not have all the information that's given. Now I have frequency, but I don't have frequency. So I can actually break it up to say H. Remember, frequency is equal to C over lambda. So I can say HC is over lambda is equal to HFO plus EK. I don't want to skip steps here. I want to show you where this comes from. I'm also now going to do this part here on the side. If I have HC over lambda, but I was told that with lambda, we are using the inverse, which is 1 over lambda. Remember, that's what we are told. I can then say HC is over 1 over lambda. But then I'm going to change this to HC is divided by 1 over lambda. To change a division to a multiplication, I do tip and tap. So I'm going to have lambda over 1. HC multiplied by lambda gives me HC lambda. And 1 times nothing remains 1. Something divided by 1 remains itself. So then I end up with Planck's constant, c being the speed of light, and then lambda. So that is then where I got that. The only tricky part that you needed to figure out here was that we're using the inverse. Where did you get that, you ask? Remember, they gave us the inverse here. So I just had to do the tip and tap there. Okay, so let's continue. So here I'm going to end up with HC lambda gives me HFO plus EK. Let me just take all of this off. Now we're going to start plugging in what we're given. But remember what I said, we have to choose 2 points. Now, I'm going to take lambda. I'm going to take some of the first one. I'm going to take where lambda is 5.00. Remember, we are measuring it in 10 to the exponent 6. I'm also going to take the kinetic energy, where it is 6.60 times 10 to the negative 19. Where are you getting this, Tops? Remember, we have to find any 2 points, and I'm going to take these ones here. I just took the first one. Remember, if you can take any point, you should get the same answer. So now we are just going to plug in. So now I'm going to write our whole formula. We have HC lambda. This is where I got my formula. We started off there, remember. Then I've got HFO plus my EK. Now we plug in. H is a constant, which is 6.63 multiplied by 10 to the negative 34. My C is the speed of light, which is 3 times 10 to the power of 8. My lambda that I'm working with is 5.00 times 10 to the exponent 6. It's equal to H is a constant, which is 6.63 times 10 to the negative 34. I am looking, they said I must calculate the threshold frequency, plus I've taken my EK, remember of that point, where I've got 6.60 times 10 to the negative 19. So just to recap on how we actually got to this, I used the formula of a straight line graph, which is y equals mx plus c. I included all the quantities for the photoelectric effect. Remember what I said, the only tricky part was remembering that we were given lambda as the inverse of lambda, and then I ended up with this formula. Now, remember, if you were to put this in your calculator, now remember to always put brackets in all your numbers. If you were to do this right, on this side, you get 9.945 times 10 to the negative 19. Just to also add on to something, my darlings, remember, if you're doing a problem and you have a lot of decimal problems, please do not round off, only round off your final answer. Because the more you round off to the nearest 10 or to the nearest whole number, you are actually increasing the bracket of your answer being incorrect. Only round off to your final answer. So if you get lots of decimals, please write all those lots of decimals. Only your final answer is rounded off, is equal to, on this side, I still have 6.63 times 10 to the negative 34. I know I am taking the long way around, but I actually want everyone to know what's happening. 6.60 times 10 to the negative 19. Now, what am I going to do? I'm going to take this number, take it over the equal sign. Remember, if something jumps the equation sign, the negative changes. I'm going to have 9.945 times 10 to the negative 19 in brackets minus 6.60 times 10 to the negative 19. If you put this in your calculator, then you should get 3.315 times 10 to the negative 19. And then you still have the 6.63 times 10 to the negative 34. But remember what I still have? I still have my threshold frequency. Now I want to make threshold frequency the subject of the formula. I'm going to have 3.315 multiplied by 10 to the negative 19 all over. You have to divide with what is irritating my threshold frequency. In this case, it's 6.63 times 10 to the negative 34. If you put this in your calculator, I get exactly 5 times 10 to the 14 hertz. But now remember, because this problem had different points with different kinetic energies as well as different lambdas, they're going to give you a bracket where you maybe a y, maybe from 4.4 or 4.8 to about 5.1 or 5.3. So there's going to be a bracket on how you could have gotten the answer. So I've got another way in how you could have done the answer. Let's see another simple way in how you could have gotten it if you didn't want to do this whole long way around. Let me summarize it here, just in case somebody's still writing there. Or you could have said, remember we were given the inverse of lambda, which is 1 over lambda. And now I'm going to take this for my graph. Why it's so important that your graph is right. The first wavelength was there. Let me just erase that so that we can see properly. If you count these spaces, it's 1.1, 2, 3, 4, 5, 6, 1.6. That is where it starts. So that is my lambda, where it initially starts. So then I can say the inverse of lambda will then give me 1.6 times 10 to the 6, and this is meters to the exponent 1. But remember, if I'm looking for lambda, I can use frequency. The threshold frequency is equal to C over the inverse of lambda. C is a constant, which is 3 times 10 to the exponent 8. And then lambda, do the inverse of that, 1.6 times 10 to the 6. And then you get 4.8 times 10 to the 14. Now remember, you can use any points and you should get more or less the same answer. Now, they're going to give you a bracket between, let's say, 4.7 maybe times 10 to the 14, maybe all the way to 5.2 times 10 to the 14, depending on if you do all of them. This is now a rough guess. I'm just guessing this. But because the points are different, the wavelengths are different, and the kinetic energies are different, then they might give you a bracket on how to work around it. But because we were looking for the threshold frequency, I could have used the equation for a linear graph to find that, which was this one here. Or I could have given that I was given lambda, I could have used this equation here. And then you should have gotten the same answer more or less.